One of the most important concepts we need for this course is the concept of vectors. This video will explain what vectors are and some of the basic vector operations we'll use as we get started with kinematics. A vector is any quantity that has both size and direction. For instance, if I say I drive 5 miles on Route 9, that isn't a vector because I didn't specify a direction. A quantity that has only a size is called a scalar. On the other hand, if I say I traveled 5 miles east on Route 9, that is a vector. Most quantities in physics are vectors. We have to account for both their size and direction. Now, let's see how to specify vectors. Here we see a log stretched out over a pond. It is oriented exactly east-west. You look out and see a shark. How would you describe where it is relative to you? There are two ways, and we will look at both. One approach is as follows. Use a tape measure to find the physical distance from you to the shark, say 20 meters. Then, whip out your pocket compass and check its compass bearing relative to you. In this case, it is 60 degrees north of east. In this class, whenever we measure angles, we will treat east as being 0 degrees and work our way counterclockwise. North would be 90 degrees, west 180 degrees, and south 270 degrees. So we could call this angle 60 degrees. So now we have unambiguously located the shark. It is 20 meters away at a compass bearing of 60 degrees. Since this description includes a size, 20 meters, and a direction, 60 degrees, it is a vector. This notation system, which contains a size and an angle, is called polar notation. In this system, the size is generically represented with the letter r, and the angle by the Greek letter theta. But this is not the only way of describing the location of the shark. Here's another. Remember, the bridge is oriented east-west. Take the tape measure and hold it at your initial location. Have a friend take the other end and walk along the bridge until they are in line with the shark. Record that distance in meters. In this case, that's 10 meters. Next, have your friend use the tape measure to find the distance from themselves to the shark. To do so, they have to hold the tape measure at 90 degrees to the bridge. We get 17.32 meters. Again, we have unambiguously located the shark. It is 10 meters east and 17.32 meters north of our position. Unlike polar notation, which used a distance and an angle, this system of describing the location uses two distances, one east-west and one north-south. This system is called Cartesian notation. In Cartesian notation, the two distances are represented as an ordered pair with the horizontal direction first, just like ordered pairs on the Cartesian plane. You might notice that this system is very similar to representing points on a Cartesian plane. Another way of writing this vector is like this: 10 I hat plus 17.32 j hat. I hat and j hat can be treated as representing the x and y directions respectively. Polar and Cartesian notation are like two languages. You can express the same vector in either notation, but which notation you want to use depends on what type of puzzle you're trying to solve. It's a bit like how the English sentence "I want an apple" means the same as the French sentence "Je veux une pomme." But if you visited Canada, where some people speak English and others speak French, you would choose one language or the other based on whom you're talking to. Just like you can translate between English and French, you can translate between polar and Cartesian. Whenever you have to convert a vector, make sure you draw it first. This is important, and we'll see why in a minute. I will take off points on your homework if you don't. Suppose you had the vector 20 meters 60 degrees in polar. How would you turn that into Cartesian? The answer is you could treat the polar vector as the hypotenuse of a right-angled triangle and apply the trigonometric ratios. The side adjacent to the angle over the hypotenuse yields the cosine of that angle. If we multiply both sides of the equation by the length of the hypotenuse, we can determine the x component of the vector in Cartesian, in this case 10 meters. Similarly, the side opposite the angle divided by the hypotenuse yields the sine of that angle. If we multiply both sides by the length of the hypotenuse, we can determine the y component of the vector in Cartesian, in this case 17.32 meters. So the overall conversion is that the vector that is expressed in polar as 20/60 degrees can be written in Cartesian as 10 I hat plus 17.32 j hat meters. To generalize this, converting into Cartesian means finding the x and y coordinates. X is always equal to r cos theta, and y is always equal to r sine theta. These are the formulas required to convert a vector from polar notation to Cartesian. What about Cartesian to polar? Let's go back to how we described the vector as the hypotenuse of a right triangle. We can find its length using the Pythagorean theorem. Since the side lengths are 10 meters and 17.32 meters, we can calculate using Pythagoras that the hypotenuse is 20 meters. What about the angle that represents the direction? Well, x and y represent the adjacent and opposite sides of this triangle respectively, which means that y over x is the tangent of angle theta, or equivalently, theta is the arctangent of y over x. Since y is 17.32 and x is 10, that means theta is the arctangent of 1.732, which is 60 degrees. So now we have demonstrated that the vector 10 I hat plus 17.32 j hat in Cartesian is represented in polar as 20/60 degrees. Again, to generalize, to translate a vector from Cartesian to polar, we apply the Pythagorean theorem to get r. r equals the square root of x squared plus y squared. And to get theta, we take the arctangent of y over x. Now, you have to be careful about that last step. Remember how I said that drawing the vector was important and had to be done first? Here's why. Look at this vector, -5 I hat minus 7 j hat. We can see this vector lies in the third quadrant. Suppose we want to find theta. We need to take the arctangent of y over x, in this case, the arctangent of -7 over -5. Our calculator tells us that is 54.46 degrees. But wait, our angle is clearly more than 180 degrees, so why did it tell us 54.46? The reason is, when you use your calculator to calculate the arctangent, the calculator will always give you an angle that lies in either the first or the fourth quadrant. But if you know that your vector lies in the second or third quadrant, you have to add 180 degrees to whatever the calculator tells you to get the right answer. This is why it is so important to draw the vector first. Your calculator will not always give you the right answer for the angle, so you have to adjust it as needed. In this case, we have to add 180 degrees to the result the calculator gave to find the real value of theta, which is 234.46 degrees. Now, let's look at some vector operations. Suppose you start at the origin. You walk 20 meters at an angle of 80 degrees. Then you turn and walk 10 meters at an angle of 206 degrees. What is your final location? To solve for this, we need to add the two vectors together. Vector addition is always done in Cartesian, so if you're given two vectors in polar, your first task is to convert them. When we convert it, we find the x component is 3.47 and the y component is 19.7. So the first vector can be written as 3.47 I hat plus 19.7 j hat. We can do something similar for the second vector. Its x component is negative 8.99 and its y component is negative 4.38. So we can write this vector as negative 8.99 I hat minus 4.38 j hat. Adding the vectors is simple. You just have to add the corresponding x components, that would give you negative 5.52 I hat, and the corresponding y components, that would give you 15.32 j hat. So your overall location is negative 5.52 I hat plus 15.32 j hat. Subtracting vectors is done analogously. If you have to subtract a second vector from the first, then you subtract the x component and the y component of the second vector from the x and y components of the first vector respectively, instead of adding them. In this case, this would yield 12.46 I hat plus 24.08 j hat. The second operation we'll look at is called scaling. Scaling is a form of multiplication. It always involves a scalar and a vector. Unlike addition or subtraction, scaling can be done in either polar or Cartesian. We'll look at polar first. Here is a vector, 120 degrees. We will multiply it by 3. To do so, we simply multiply the size of the vector by 3, leaving the direction unchanged. This yields 120 degrees. We see that the scaling operation made the vector longer, but the product points in the same direction as the original. What if we multiplied the original vector by something less than 1, like 0.8? Again, we multiply the scalar by the size, and we get a new vector that is shorter than the original, but still pointed in the same direction, 1.6, 120 degrees. How about if we multiplied the original by a negative number, like negative 2? In this case, we would perform the same operation. We would yield negative 4, 120 degrees. In polar, we don't usually write the size of the vector as negative. So instead, we write the size as positive and add 180 degrees to the direction, which describes the same result. So negative 4, 120 degrees is the same thing as 4, 300 degrees. What if you had to scale a vector in Cartesian? Take this vector, 4 I hat minus 3 j hat. In Cartesian, we multiply both the x component and the y component by the scale factor in order to get the required result. So we would multiply the 3 by both coordinates to yield 12 I hat minus 9 j hat. This video introduced vectors and explained how to add and scale them. These few operations will be enough to get us through the first 2 topics of this course. Further vector operations will be introduced as we proceed through the course.